All right, let's calculate the pH of a solution in which 20 milliliters of 1 molarity sodium hydroxide is added to 50 milliliters of 1 molarity of acetic acid. And I give you the Ka of acetic acid to be 1.8 times 10 to the negative fifth. Okay, is this a single solid or is this a reaction? It's a reaction. Okay, is it a neutralization or is it a buffer? It's a neutralization. I got an acid and a base. Now, we said it's not a buffer, but it may be a buffer in the end. When you start reacting weak and strong species, buffers are something that can form later on. But on the surface right now, all it is a pure neutralization reaction. Now, can we make any ideas of where the pH should be when we get finished? Well, since I have a large amount of acid compared to the amount of base that I'm adding, we would assume that the pH would be on the acidic side when we get finished with this calculation. It would be before the equivalence point. Calculate the millimoles of each component first is what we're going to do since it's a neutralization. So you have your acetic acid, which is your 50 times 1, which is 50 millimoles, and your sodium hydroxide, which is 20 times 1, which is 20 millimoles. Next step is your neutralization. So you got to write your reaction. It's important that you write your reaction and get the right products. Okay, so in essence what we're talking about is acetic acid plus sodium hydroxide. So that proton is going to come exchange with that sodium, and we're going to end up making sodium acetate. Okay, so I get acetic acid plus sodium hydroxide gives me sodium acetate and water. It's very important that you can write the reaction for you to know what the product is so you can make decisions later on. Next step, do my millimole table. Okay, so I set up my millimole table. So I have my initial millimoles, which is 50 for the acetic acid, 20 for the sodium hydroxide, and I have no source of sodium acetate before the neutralization, so I have 0. Then I need some change. Okay, that change is going to be equivalent to that limiting reagent, which in this case can be sodium hydroxide. So I'm going to have 20 millimole difference in change, and since it's on the reactant side, it's going to be minuses. On the product side, it's going to be plus. Okay, which means then after neutralization, I end up having 30 millimoles of acetic acid, 0 millimoles of sodium hydroxide, all of it was consumed, and 20 millimoles of sodium acetate. Okay, so I have my components of acetic acid and sodium acetate. They're the ones that can affect my pH of my solution. So, next question. New concentrations of species affecting pH. So now we're going to figure out those two components that could be affecting my pH. Will they affect it? What is acetic acid? Okay, it's an acid. What kind of acid? A weak acid. Can that affect the pH of a solution? The answer is yes, it can. So that's something to worry about. Sodium acetate, what is that? It's a salt. Okay, a soluble salt. What kind of soluble salt? A basic salt. Okay, which is what we expected, because remember, I got a weak acid and a strong base. We said if that's the case, what kind of salt should I make? I should have an excess of strength and base, so I should form a basic salt, which is what we do. Okay, so I have a basic salt. Can that affect the pH? The answer is yes. Okay, so we have our weak acid and our basic salt. Now what we're going to look at is say, how are they reacting? Okay, one or two things could be happening at this point. I could either be a case where I have another neutralization reaction, where I have an acid and a base reacting again, or it could be a case, since I got an acid and a base here, it could be a buffer there. Now, in our purposes, in our class right here, we're not going to see another neutralization. That's usually going to happen if you get diprotic species, etc. And you would handle it just as I'm doing these calculations here. And I would say, okay, I got a neutralization, so I would do another neutralization, come up with my new concentrations, and then go on from there. You know, once again, what species affect pH, etc. So the same process I'm teaching you here, you can use when you get to that point in, say, quantitative analysis, where you have to do and handle a second neutralization reaction. But that's not something we should run into in this class. So let's look at what we have here. We have acetic acid and sodium acetate. And you notice on the sodium acetate part that we have a conjugate base. So what we have here is acetic acid and sodium acetate, which is a buffer. So I got to handle both of them. I need both of them, both components, to do a buffer problem. Okay? This is what's going to happen when you do your titration, your pH versus your titrant, all the way up to the equivalence point, all the way up here, you're going to end up getting a buffer. All those calculations are going to be buffer calculations all the way up to the equivalence point. Okay? All the way up to the equivalence point, there will be buffer calculations. Now, as you get closer to the equivalence point, it's going to get more dilute, and then the buffer capacity falls apart. Okay? But most of your calculations are going to be down here where it's a true buffer. Okay? Not a problem in this course the way that we have it designed. So, what I need to do now is figure out my new concentrations of the things I care about, which we said I care about the acetic acid and I care about the sodium acetate, because what I have here is a buffer. So to figure out my concentration of my acetic acid, I'll take my 30 millimoles from my neutralization divided by my total volume, which is 50 plus 20, which is 0.4286 molarity. I'll then take my sodium acetate, which is 20 millimoles, divide that by my 50 plus my 20. Notice my millis all cancel out, leaving me a molarity of 0.2857 molarity. Okay? Now we're at the same point we did when we talked about buffer solutions. It's just like I rewrote this problem now and said I got 0.4286 molarity of acetic acid and 0.2857 molarity of sodium acetate. What's the pH? So at this point we do our hydrolysis. Now how do we handle the hydrolysis of a soluble salt in an acid? Okay, when we have a buffer component, a buffer system. We take that soluble salt and do what? Do the dissociation first, and then we do the hydrolysis of the acid, do our ice table, and continue on from there. So, next step will be hydrolysis. We'll write the soluble salt first, which is sodium acetate breaks up into sodium ions and acetate ions, which are the same concentration since it's 1:1. Then I'll write my acid hydrolysis, which is my acetic acid, gives me hydronium ions and acetate ions. Anytime I write an equilibrium there, I'm going to go ahead next with my ice table. I have my initial of my acetic acid, which is 0.4286. 0 for the hydroniums, assuming nothing from the water. And since I write it this way for my soluble salt on top, why? Because I wanted to remind me to put in that 0.2857 for the acetate. Remember, this is a buffer, so I have some of that soluble salt that I got to account for. Then we now figure out which way this reaction is going to shift. It's going to have to shift to the right because I got 0 hydronium, which means I got minuses on my reactant side and pluses on my product side. I need some relationship between the substances. It's all 1:1, so we're going to say X change, so it's X, X, and X. Add them up for my equilibrium. I get 0.4286 minus X, X, 0.2857 plus X. Then we ask ourselves an important question. That question is, how are these related? And the way that we wrote this problem, it's related through Ka. So I'll write my Ka expression. Ka is your hydronium ion concentration times your acetate concentration divided by your acetic acid, which is X for hydronium, 0.2857 plus X for your acetate, and 0.4286 minus X for your acetic acid. I want to get rid of the X's. I can do that because this is a buffer system and I have similar concentrations, which means then I can get rid of the plus X and minus X, which leaves me X times 0.2857 divided by 0.4286 equal to 1.8 times 10 to the negative fifth, which is the Ka. I need to multiply both sides by 0.4286, divide by both sides by 0.2857, which gets me the following. 0.4286 times 1.8 times 10 to the negative fifth divided by 0.2857 gives me 2.7 times 10 to the negative fifth molarity. Now, an important question here is, what does X represent in this problem? We got it set up to equal the hydronium ion concentration, which is important because if I'm dealing with a base, it would be hydroxide, okay? Which then tells me that pH is equal to negative log of hydronium, which is equal to negative log of 2.7 times 10 to the negative fifth, which is 4.57. Now, since we were before the equivalence point, we expected that the pH would be less than 7, and it is. And we have a 4.57 pH. As we said, all the calculations up to that equivalence point is going to be a buffer system when you're dealing with a weak and a strong species. Okay, let's calculate the pH of a solution in which 50 milliliters of 1 molarity sodium hydroxide is added to 50 milliliters of 1 molarity of acetic acid. Is it a single solute or is it a reaction? It's a reaction. Is it a neutralization or a buffer? It's a neutralization. Before we get into the problem, let's see where we are at this juncture in this calculation. I got 50 milliliters of 1 molarity of sodium hydroxide and 50 milliliters of 1 molarity of acetic acid. It's all 1 to 1, so we're at the equivalence point. Since I'm at the equivalence point, and this is an acid-base reaction, does that mean I know what the pH is? Should I say the answer is pH is equal to 7 because I got an acid base and I'm at the equivalence point? I hope your answer is no. Okay, why no? That's because I got a strong base and a weak acid. Remember, strong is the only scenario where it will be a pH of 7. So this pH will not be at 7. It's going to be something different. Okay, so we're going to have to do the calculation to figure out where is the pH in this calculation. So first step, calculate the initial millimoles of each component. Millimoles of acetic acid is 50 times 1, which is 50 millimoles. I got sodium hydroxide, which is 50 times 1, which is 50 millimoles. Neutralization reaction. Got acetic acid and sodium hydroxide, which gives me sodium acetate plus water. Now, since I have a weak acid and a strong base, we expect then what kind of salt should be formed? A basic salt. So we expect this reaction, the equivalence point, to be a greater than 7 because of the fact that I'm forming a basic salt. Okay, so we are anticipated that the pH will not be 7 at the equivalence point. It's going to be something greater than 7 because of what's happening in our reaction. We do our millimoles. I got 50 for acetic acid, 50 for sodium hydroxide, none for sodium acetate. My change will be 50, so I get minus 50s on the reaction side, plus 50s on the product side. 0 for my sodium hydroxide, 0 for my acetic acid after neutralization, and 50 for sodium acetate. So I have 0, so I'm at the equivalence point. Okay, but that product being sodium acetate, what's going to dictate where the pH is? So I want to find the new concentrations of species affecting pH. So I ask myself, what is sodium acetate? It's a salt, a soluble salt. What kind of soluble salt? A basic salt. So is that something that can affect the pH? The answer is yes. That's going to affect the pH, and that's what's going to stop it from being pH equal to 7. So I need to find out my new concentration. So it would be my 50 millimoles over my total volume, 50 plus 50, which is 0.5 molarity. Now the problem is just like when I introduced to you soluble salts. Okay, it's just like I said, I got a 0.5 molarity solution of sodium acetate. What's the pH? Well, what do? We take that salt, we do the dissociation, then we figure out which ion is going to affect the pH, which we already talked about, which is the acetate. Okay, so then I got to do that acetate hydrolysis. Okay, so continuing on with the problem. Okay, my hydrolysis, I do my dissociation first. We now know that I got 0.5 sodium and 0.5 acetate. We know that acetate is something that can affect the pH. It's a base. Okay, so then we have to take that species, that acetate species, and now write the hydrolysis of that species, which gives me acetate, which gets me acetate plus water, gives me acetic acid and hydroxide. Then since I got an equilibrium, I got to write my ice table, which is 0.5 for my acetate, which we just got from the calculation above. Notice I have 0 for my acetic acid. Yes, there was some written in the initial problem at the top, but remember we neutralized all that, so there's none of that, and then all that's gone. The only acetic acid that's going to come is from this hydrolysis here, whatever forms, which is going to be mold to mold the same as the hydroxide. 0 for hydroxide. It's going to have to go to the right, so I got minuses on my reactants and pluses on my product side, and x to x to x. Add them up, 0.5 minus x, x, and x. Now here comes an important question. This is where mistakes happen and careless mistakes occur. Okay, how are these three things related the way that we wrote this problem right here? KB. They're a KB problem. Remember, in the problem they gave us initially what? KA. So what am I going to have to do from here to get from KB to KA? I'm going to have to go through KW. So KB is equal to KW divided by KA, which is 1 times 10 to the negative 14th divided by 1.8 times 10 to the negative 5th, which gives me 5.6 times 10 to the negative 10th. That's is equal to my concentration of my acetic acid times my hydroxide concentration divided by my acetate ions. Plug in my values, x, 0.5 minus x. I can do the quadratic formula or try to get around that. Let's look at it. I have now 0.5, which is the same thing as saying 5 times 10 to the negative 1. Compare that to my KB, which is 10 to the minus 10th. That's 9 powers of 10 difference. We said if it's 3 or greater, we can neglect x. So therefore, I can get rid of my x. Which gives me x squared over 0.5 equal to 5.6 times 10 to the negative 10th. Multiply both sides by 0.5, which gets me 2.8 times 10 to the negative 10th is equal to x squared. How do I get rid of the x term? That would be the square root of both sides. And then do my calculation. X is equal to 1.7 times 10 to the negative 5th molarity. Now at this point, what do we do? Yes. What does x represent in this problem? Remember, x in this problem represents what? Hydroxide concentrations. Two important parts where people can make mistakes, careless mistakes, is right here with the Ka, Kb, and right here with the hydroxide. Okay, that's where mistakes happen. Okay, make sure you're checking for those. So then I have my hydroxide concentration, which we say is pH is equal to 14 plus the log of hydroxide, 14 plus the log of 1.7 times 10 to the negative 5th, which gets me a pH of 9.22. Remember, this is at the equivalence point. Okay, at the equivalence point. Okay, so at the equivalent point, 9.22. It's not 7. Yes, my acid and base are consumed, but I formed it as a basic salt, so therefore my pH is much higher than 7. Notice at the equivalent point, the pH is not 7 because we're talking about a strong, weak component. So as you're doing your titration curve, down here we have a buffer, and right here my equivalence point in this particular case was equal to 9.22, not 7. Okay. What we're going to do now is figure out what happens above the equivalence point. Calculate the pH of a solution in which 51 milliliters of 1 molarity sodium hydroxide is added to 50 milliliters of 1 molarity of acetic acid. So notice that I'm a little bit beyond the equivalence point now. I have excess of base in this problem. Okay, following our procedure, single solute or reaction. Reaction. Is there a neutralization or is there a buffer? Neutralization. So we need to now go and do our calculations. So first step would be millimoles of each component. 50 times 1 is 50 millimoles of acetic acid. 51 times 1 is 51 millimoles of sodium hydroxide. Next step is your neutralization. Which gets me acetic acid plus sodium hydroxide gives me sodium acetate. Do my millimoles table. 50 and 51 for the sodium hydroxide. 0 for my sodium acetate. I need to figure out what is my limiting reagent, which is going to be that 50 of the acetic acid. So I get minus 50 on my reactant side, plus 50 on my product side, which leaves me 0 for acetic acid, 1 for sodium hydroxide, and 50 for sodium acetate. So the sodium hydroxide and sodium acetate is where my pH can come from. Next step, new concentrations of the species affecting pH. So let's look at sodium hydroxide. Can that affect the pH? Yes. Why? What is it? It's a strong base. So yes, that can affect the pH. What about sodium acetate? What is that? That's a soluble salt. What kind of soluble salt? The basic salt. Can that affect the pH? Yes. Okay. So I have both these components can affect it. So let's think about what we have here. I got a strong base. That means for every drop I add, I'm adding hydroxide, and I have a basic salt. For every drop of way less than 5%. How much do we think that basic salt is really contributing to the overall basicity in comparison to that strong base? Not a lot, very little. So in essence, what we can do then, since I got a strong base and a basic salt, we're saying that basic salt is so small I can neglect it. And we're going to be able to show you that because in the previous problem we just did, it was at the equivalence point, which was a basic salt only calculation, and the pH was 9.22. We're going to see where the pH is here, neglecting it, and see that it's drastically different in pH, much higher than that salt was. So we can easily neglect it. And you also got to realize that basic salt is going to shift in equilibrium because I have some of this strong base that's coming. So it's going to shift that equilibrium, so it's going to be even less coming from that basic salt, hydroxide coming from that basic salt. So whatever numbers I show you, really it's worse than that because of the fact of the shift. Okay, so the hydroxide from the basic salt is extremely small as compared to the strong base, therefore we're going to neglect it. Okay? Now, when you start, asking yourself questions about what the product's being left after neutralization, you're going to have certain scenarios that are going to occur. Okay, one you already realized. Okay, when you actually get to that point and you got some components left, you're going to get a case where I have a weak species, say a weak acid, and a basic salt. Okay, which in essence is the buffer, right? So you're going to get a buffer situation, okay? Or it could be the opposite. You could have a acidic salt and a weak base. Okay, so you could get some buffer. Okay, so in that case, you got to handle both, right? You need to handle the weak acid and the basic salt, or the acidic salt and weak base. You got to handle both components, okay? Where you got to now. Could be a case where you get a strong base and a weak base, okay, which is like the scenario we have right here. When you get a strong base and a weak base, we're going to worry about the strong base and we're going to neglect the weak base. Okay? Now, what happens if I get a strong acid and a weak acid? What do you think is going to happen in that scenario? Same thing. I'm going to worry about the strong acid, and I'm going to neglect the weak acid. Other scenarios you may run into. I may get a strong acid and a strong acid. Well, both of them are strong, so they're both doing 100%. So this is contributing some hydronium ion, right? Every drop. This is contributing some hydronium ion every drop. So how do you think we're going to handle a case if I get strong acids on both sides? Okay, I have some reactant left over and I got some product. Well, you're just going to add them up, okay, because it's just hydronium. Okay, so you add those up and make up your concentration of hydronium and figure out the pH. Strong base. What do you think is going to happen there? Same thing. I'm going to get some hydroxide coming from here, some hydroxide coming from there, okay, from those two components. I'm going to add them up, once again, and figure out my pH. These are the scenarios that you're going to run into. You're going to run into a buffer. Okay, you're going to run into buffer problems. You're going to run into a strong, weak base. So you just worry about the strong one. You're going to run into a strong acid, weak acid. Worry about the strong acid. You're going to run into strong acids. Just add up to hydroniums. Strong base, add up to hydroxides. Is it possible that I could run into something where I have an acid and a base? Yes. That's possible, okay? So at that point, what you have then is a neutralization again. So at that point, you have a neutralization to do that you have to do again. So I have an acid and a base. It's not a buffer, okay? Well, at that point, I got to do another neutralization, figure out my millimoles of what's left, and go on from there. Is that something that we're going to run into in this class? And the answer is no. Okay, we're not going to run into that. That's going to be something we're going to start when you get into quantitative analysis and all that. Right now, we're doing simple monoproduct stuff. in this course. So yes, that's possible. It's not something you're going to run into in this class. So the ones that you're going to run into are right here. Okay, that's what you're going to run into. Continuing on with our problem, we're saying that I'm only going to worry about the base. So then I'll do my calculation for my sodium hydroxide, which is my millimoles, divided by my total volume, which is 9.9 times 10 to the negative 3 molarity. Since it's just a strong base, you do hydrolysis like we've done in the past. Okay, so I'll take that, break my sodium hydroxide, which gives me sodium and hydroxide, which gets me 9.9 times 10 to the negative 3rd molarity of both. Okay, want the pH. pH then will be 14 plus the log of hydroxide, gives me 14 plus the log of 9.9 times 10 to the negative 3rd, which gives me a pH of 12. Now notice, when we did the previous problem, okay, in the previous problem, notice that we had a pH of 9.22, okay, which our OH concentration of 1 times 10 to the 1.7 times 10 to the negative 5th. Now, in comparison to that OH that's coming from my sodium hydroxide, it's very small. If I add those two numbers up significant figure-wise, I still have 9.9 times 10 to the negative 3rd. So it's not contributing a large amount, which means I can neglect it. But also realize, since you're dealing with an equilibrium of that acetate ion, remember that I have a source of hydroxide coming from that strong base, which means that this equilibrium is going to have to shift to the left, okay, because now it's messing up the equilibrium, which means the concentration of my OH from this equilibrium is going to be even less. So the amount of OH coming from this equilibrium is going to be less than 1.7 times 10 to the negative 5th. So it's going to be even worse than what it looks like here, okay? So you can see that 9.22 versus 12, that amount of hydroxide coming from that soluble salt is not enough to shift this equilibrium and cause it to be something to worry about, okay? So in essence, all we're going to do, we won't even worry about that basic salt and only worry about the sodium hydroxide. Homework 39 deals with calculating pHs of weak, strong stuff.